If you've had some exposure to relational databases, you've probably come across the term normalization. But what is normalization? Why do we do it? How do we do it? And what bad things can happen if we don't do it? In this video, we're going to explore database normalization from a practical perspective. We'll keep the jargon to a minimum, and we'll use lots of examples as we go. By the end of it, you'll understand the so-called normal forms from first normal form all the way up to fifth normal form. And you'll have a clear sense of what we gain by doing normalization and what we lose by failing to do it. This is Decomplexify, bringing a welcome dose of simplicity to complex topics. Data. It's everywhere, and some of it is wrong. By and large, even a good database design can't protect against bad data. But there are some cases of bad data that a good database design can protect against. These are cases where the data is telling us something that logically cannot possibly be true. One customer with 2 dates of birth is logically impossible. It's what we might call a failure of data integrity. The data can't be trusted because it disagrees with itself. When data disagrees with itself, that's more than just a problem of bad data. It's a problem of bad database design. Specifically, it's what happens when a database design isn't properly normalized. So what does normalization mean? When you normalize a database table, you structure it in such a way that it can't express redundant information. So, for example, in a normalized table, you wouldn't be able to give customer 1001 2 dates of birth, even if you wanted to. Very broadly, the table can only express one version of the truth. Normalized tables are not only protected from contradictory data, they're also easier to understand, easier to enhance and extend, and protected from insertion anomalies, update anomalies, and deletion anomalies. More on these later. How do we determine whether a table isn't normalized enough? In other words, how do we determine if there's a danger that redundant data could creep into the table? Well, it turns out that there are sets of criteria we can use to assess the level of danger. These sets of criteria have names like first normal form, second normal form, third normal form, and so on. Think of these normal forms by analogy to safety assessments. We might imagine an engineer doing a very basic safety assessment on a bridge. Let's say the bridge passes the basic assessment, which means it achieves safety level 1, safe for pedestrian traffic. That gives us some comfort, but suppose we want to know if cars can safely drive across the bridge. To answer that question, we need the engineer to perform an even stricter assessment of the bridge. Let's imagine that the engineer goes ahead and does the stricter assessment, and again the bridge passes, achieving safety level 2, safe for cars. If even this doesn't satisfy us, we might ask the engineer to assess the bridge for safety level 3, safe for trucks, and so on. The normal forms of database theory work the same way. If we discover that a table meets the requirements of first normal form, that's a bare minimum safety guarantee. If we further discover that the table meets the requirements of second normal form, that's an even greater safety guarantee, and so on. So let's begin at the beginning with first normal form. Suppose you and I are both confronted by this question. You might answer John, Paul, George, and Ringo. I might answer Paul, John, Ringo, and George. Of course, my answer and your answer are equivalent, despite having the names in a different order. When it comes to relational databases, the same principle applies. Let's record the names of the Beatles in a table, and then let's ask the database to return those names back to us. The results will get returned to us in an arbitrary order. For example, they might get returned like this, or like this, or in any other order. There is no right order. Are there ever situations where there's a right order? Suppose we write down the members of the Beatles from tallest to shortest, like this. We title our list Members of the Beatles from Tallest to Shortest. In this list, it's not just the names that convey meaning. The order of the names conveys meaning too. Paul is the tallest, John is the second tallest, and so on. Lists like this are totally comprehensible to us, but they're not normalized. Remember, there's no such thing as row order within a relational database table. So, here we have our first violation of first normal form. When we use row order to convey information, we're violating first normal form. The solution is very simple. Be explicit. If we want to capture height information, we should devote a separate column to it, like this. Or even better, like this. So far, we've seen one way in which a design can fail to achieve first normal form, but there are others. The second way of violating first normal form involves mixing data types. Suppose our Beatle height dataset looked like this. If you're accustomed to spreadsheets, you'll be aware that they typically won't stop you from having more than one data type within a single column. For example, they won't stop you from storing both numbers and strings in a column. But in a relational database, you're not allowed to be cagey or ambiguous about a column's data type. The values that go in the height in centimeters column can't be a mix of integers and strings. Once you define height in centimeters as being an integer column, then every value that goes into that column will be an integer. No strings, no timestamps, no data types of any kind other than integers. So, mixing data types within a column is a violation of first normal form, and in fact, the database platform won't even let you do it. A third way of violating first normal form is by designing a table without a primary key. A primary key is a column or a combination of columns that uniquely identifies a row in the table. For example, in the table Beatle height, our intention is that each row should tell us about one particular Beatle, so we ought to designate Beatle as the primary key of the Beatle height table. The database platform will need to know about our choice of primary key, so we'll want to get the primary key into the database by doing something like this. With the primary key in place, the database platform will prevent multiple rows for the same Beatle from ever being inserted. That's a good thing, because multiple rows for the same Beatle would be nonsensical and perhaps contradictory. Obviously, a Beatle can't have two different heights at once. Every table we design should have a primary key. If it doesn't, it's not in first normal form. The last way of failing to achieve first normal form involves the notion of repeating groups. Suppose we're designing a database for an online multiplayer game. At a given time, each player has a number of items of different types, like arrows, shields, and copper coins. We might represent the situation like this. The player's inventory is what we call a repeating group. Each inventory contains potentially many different types of items, arrows, shields, copper coins, and so on. And in fact, there may be hundreds of different types of items that a player might have in their inventory. We could design a database table that represents the inventory as a string of text, but this is a terrible design because there's no easy way of querying it. For example, if we want to know which players currently have more than 10 copper coins, then having the inventory data lumped together in a text string will make it very impractical to write a query that gives us the answer. We might be tempted to represent the data like this. This lets us record up to 4 items per inventory. But given that a player can have an inventory consisting of hundreds of different types of items, how practical is it going to be to design a table with hundreds of columns? Even if we were to go ahead and create a super wide table to hold all possible inventory data, querying it would still be extremely awkward. The bottom line is that storing a repeating group of data items on a single row violates first normal form. So what sort of alternative design would respect first normal form? It would be this. To communicate the fact that Trev73 owns 3 shields, we have a row for player Trev73, item type shields, item quantity 3. To communicate the fact that Trev73 also owns 5 arrows, we have a row for player Trev73, item type arrows, item quantity 5, and so on. And because each row in the table tells us about one unique combination of player and item type, the primary key is the combination of player and item type. So let's review what we know about first normal form. Number 1, using row order to convey information is not permitted. Number 2, mixing data types within the same column is not permitted. Number 3, having a table without a primary key is not permitted. And number 4, repeating groups are not permitted. Next up, second normal form. Let's look